Assalamu alaikum everybody, this is the task 4 for microprocessors and microcontrollers. In this task we are going to talk about assembly programming. As you can see here, we will start with talking about the Pentium registers, arithmetic operations, logical operations, then finally loops and jumps. And I advise you to see the solved exercises where there is a lot of exercises solved for you along with the mock test. So first of all, inline assembly. Inline assembly means we are writing the assembly programs on the Microsoft Visual C++ program. Okay, so we are writing this information in Microsoft Visual C++, the same that we used in C++ previously. So we start our instructions by doing underscore ASM, then we write our instruction. If we are writing a block of instructions, then we use underscore ASM with a bracket. Now for now, since we don't have a lab, I'm not going to bother you with doing the programs. We are going to do it all theoretically on the papers. So the data types, we usually have an integer which is 4 bytes, we have unsigned integer which is 4 bytes, we have a short which is 2 bytes, and we have double underscore integer 8 which is 1 byte signed, and character which is 1 byte for character. So usually we use double underscore integer 8. Okay, double underscore integer 8 for 8 bits, short for for 8 bits, short for 16 bits, and integer for 32 bits. It depends what we are going to program. Now if you are using an Intel microprocessor which is a 32-bit, we are going to use integer. If we are using an 8086 which is 16 bits, we are going to use short. If we are trying to address AL, AH, BL, BH, CL, CH, DH, DLDH, which are 8 bits registers, then we are going to use double underscore integer 8. So first of all, here's the move instruction. This is our source and the destination. Move instruction copies the source information and puts it into the destination. Copies means the source contents are not changed. So the source contents are not changed. So for instance, consider an array that has double underscore integer 8. This means each value inside this array is 8 bits. Each value is 8 bits. If it was short, then it will be 16 bits. Move array B to AL will take the first element in array B, put it in AL. This means AL will have a contents of 10. Move array B plus 1 into AL. This is the first element. This is element 0. This is element 1. This means I will take 20, put it into AL. Now the next one, short. Move W array W plus 2 means we are going to go to the third location and copy 2 bytes into AX. Why third location? Remember 0, this one will be stored in 0, 1, 2, which is the third location, and we are going to copy these 2 values. If we are going to say plus 1, okay, if we are going to say plus 1, then this means this is a different story, because in plus 1 we are going to say this is the value stored in 0. We are going to take 1, 2, 7, 8, which is the Little Indian convention, which we talked about in task number 3. Exchange instruction. Exchange instruction will basically swap the values of 2 registers, which is the source and destination. Swap means change the values. The source will be the destination and the destination will be the source. Then we have increment and decrement. Increment adds by 1, decrement subtracts by 1. Add and subtract. Add and subtract. The add instruction will add the source to the destination and stores the result in the destination. So 5 plus AL and store the result in AL. AX plus BX and store the result in BX. AL plus a memory location and store the result in the memory location, and so on. subtract will do the same. It will be AL minus 5 and store the result into AL. Okay, so source minus destination subtracts the source operand from the destination operand. So it is AL minus 5 store the result into AL. BX minus AX store the result into AX, and so on. So here is the direct operand example, and here is an indirect operand example. Consider a character string which is A, B, C, D, E, F, G between two quotations. This is a string. Move A string to DL. When you say move without any addressing, this means the first character will be moved. Now move A string plus 5, this means this is 0, 1, 2, 3, 4, 5. So we are going to move F into DL. Load effective address gives you the actual address. It will not move the contents, it will give you the address. So load effective address, okay, load effective address of EBX A string means where is A string stored in, where is the starting address of this string. It is 200, so we are going to put 200 into BX. Okay, over here load effective address of the string into BX, add to EBX5, move EBX to DL. So I'm going to take the contents of memory location specified by extended BX and put it into DL. So 0, 1, 2, 3, 4, 5. I'm going to take the value of F, put it into DL. Adding 16-bit integers, 8-bit integers first. We are going to create a double score integer 8 A list array, and this is the sum. Then load effective address of A list. You can see here we moved the effective address, or we moved the first in AL. The first element, which is 10, is in AL. Increment EBX. EBX now is pointing to 20. Add 20 plus 10, which is 30. There is a destination. The result is stored in the destination. Increment, add once more, and store the result. Same idea over here, but when it's a 16-bit, instead of increment adding by 1, we need to add by 2 to get the second number. If it's a 32-bit, we add by 4, then by 8. Now in two-dimensional arrays, it's the same idea. Let's say you have an array which is a 2 by 5. You put the elements behind each other. For the computer, for an assembly language, we don't have two-dimensional arrays. Instead, we have one-dimensional array, but we know the size of the row. Number of rows are 2, number of columns are 5. The important part is the number of columns, because from there you can get the first element of the second row. Integer multiplication and division. You have only the source. So if I say mul AX, okay, mul AX, this means the source is being multiplied by AL. Let's say I have an instruction mul BL. Mul BL means the source BL is multiplied by AL. If I say mul CX, the size, okay, pay attention, it's the size. If it's a CX, it will be multiplied by AX. If it's extended DX, let's say, it will be multiplied by extended AX. So this is basically the idea over here. And where do we store the results? If we are multiplying a byte, we store in AX. If we multiply AX, then we are going to store in AX extended with DX. If we multiply EAX, we are going to store the result in extended AX and extended DX. So division is the same. If I divide 7 by 2, I'm going to get 3, and the quotient, or the remainder, is 1. So if I say div the divisor, this means the divisor is a byte, which is, let's say, BX. The dividend, this is the numerator and the denominator. Numerator and the denominator. The dividend, it's the other way around. AX divided by the divisor. So this is the dividend, which is the numerator, and this is the denominator. تمام. So هذا البسط وهذا هو المقام بالعربي، البسط والمقام. This means if I'm going to say div cx means that dx ax are in the numerator, the denominator is cx, result will be stored in ax and dx, quotient and reminder, quotient and reminder. Then we have the jump and loop. In jump and loop instructions, you need to remember that you need, if there is a jump, there is always a label. You need to jump to a certain label in order to do the jump and loop. Here are some examples about the loop instruction. In the loop instruction, the most important part is cx. cx acts as your counter. How many times you want to do a loop, then you need a counter. Every time you say loop, you decrement cx. If cx is greater than 0, you loop. When do you decrement? Just when you say loop, you decrement, and then you are going to check if cx is less than or not. This is an example on looping. Compare instruction. Compare is simply like subtract, but it will not store the result, and we use it a lot for jump instruction. These are some examples for using jumps and comparisons. We have the jump if 0, jump if equal, jump if not 0, not equal, carry, not carry, jump if cx is equal to 0, ecx is equal to 0, jump if parity, jump if above, jump if below or equal, jump if above or equal, jump if not below, if below, if not above or equal, if below or equal or not above. These are all the things that you can imagine for jumps and all the situations. We can use them all for writing our programs. Again, I put a lot of examples for you in the exercises. You can see them all over there. This is an example to write an assembly code to find the smallest value between 3 registers. Another example to add sensors. This example is a very good example. This is the conditional loops, which we have loop if equal and loop if 0. You will have 2 conditions. Not only cx is greater than 0, you will also check the 0 flag for the situation and see what is the answers. I will have more explanations for you on this once we start the task and you read all this information. I will go and another videos and explain the details these examples. But first I need you all to read the information so we get familiar with it, then we will go into more details. We have the logical instructions, and as you know, it's all bitwise operations. So AND EAX EBX, it will AND the contents of EBX to EAX and store the result into EAX. And the ANDing is bitwise, so 1 and 1 is 1, 1 and 0 is 0, and so on. OR operation is more or less the same, but it will OR the bitwise operation. We have the XOR, XOR, and NOT, and then we have the shifts and rotates. First we have shift left, means shift the bits by 1 bit to the left, shift the bits by 1 bit to the right for shift right, and the bit will be sent to the carry. Then we have shift arithmetic. In shift arithmetic left, it's the same as shift left. There's no difference, but shift arithmetic right, the sign bit will remain the same. The most significant bit, which is which represents the sign bit, will always remain the same in order to preserve the sign. Then we have the rotate. In rotate, the bits will keep rotating as many times as you want. Rotate right, rotate left, rotate carry right, rotate carry left. In rotate right, in rotate left, you are going to rotate all the bits to the left. In rotate carry left, you are going to rotate them including the carry bit. Rotate right, you are rotating the bits to the right, and the carry bit is not included. In rotate carry right, I hope you can see it, it's rotating within the carry also. This is mainly the information that we need to know. I have put a lot of samples for you in the sample exercises for you to check out, and I'm going to have another video for you once we start task 4 to discuss more about these examples. Hope to see you all soon, and stay safe. Let's hope we see you all in semester 1 2021 and 2022. That's all for now. Thank you.